Okay, so with these, okay, the big thing is, like, the toughest manipulation of V equals d over t is for t, because we have to actually move two things in order to get that. All right, in this one here, we have the constant speed of sound, 343 meters per second, okay, which sounds fast, but we've obviously all had the experience of like seeing something happen and then a moment later actually hearing the sound of it. If you've ever been like at a track meet or something like that, you have to, you see the smoke long before you hear the sound of the shot. Okay, thunder's the same way. You see the lightning long before you hear the thunder. Okay, unless of course the lightning and the thunder are in the same place. Okay, so if you're right next to the lightning strike, it's a much different experience. Okay, so how much time does it take in seconds? So we're looking for t, okay, and we know that it's traveling 1 mile, which is 1,609 meters. Okay, so V equals d over t. If I want to solve for t, I can't solve for something if it's on the bottom of an equation, so I need to move it to the other side. Since I'm dividing by it, I perform the opposite operation. Multiply, it's gone. What I do to one side, I do to the other. T times V solves for D, and then I want to solve for T. So, since I'm multiplying by V, I do the opposite, I divide it, it comes over to the other side underneath. Okay, so now we have T equals D over V. Alright, so that's going to be 1,609 meters divided by 343 meters per second, and that's going to give us our 4.69 seconds. Okay, so if lightning struck a mile away from you, okay, you'd be able to count to almost 5 before you would hear the sound of the thunder. Okay, and that's always how you can tell. Generally, the rule is if you multiply the seconds by by 300, it's 3 kilometers. It's basically 0.3. Sorry, by 30. Okay, you'd have it. So. 343 meters per second. Okay, so 1 kilometer takes about 3 seconds. Okay, so that sort of making sense? Okay. All right, let's have you guys try. Okay, this is a good one, because we're going to do something else with this one afterwards. I'm going to say looked away for a second to tune the radio, not what most people are not looking at the road doing. Yeah, once you've driven a little bit, you'll realize what it is too. Just don't be the person doing it. Texting drivers. All right, so for this one here, okay, they once again give us the speed, 27 meters per second. Okay, driver looks away from the road for 2 seconds, or 2 seconds. I don't know why it says that, but 2 seconds. Okay, how far does the car go during this time? So now we're looking for D. Okay, well, V equals D over T. If I want to get D by itself, I have to move T. The opposite of divide is multiply, so I multiply both sides by T. 2 times 27 is 54 meters. Is that a long way? It's about 1/4 of the school zone. School zone's just a little over 200 meters long. Okay. Those little thumps you hear as you're traveling along through the school zone are bad. Okay. Because if you've looked away and traveled 1/4 of the school zone, you have probably run over somebody along the way. Okay. You should really pay attention to the road. Okay. Now, here's your life lesson for today. Is texting and driving a good idea?
No.
Okay. Everybody generally agrees on that. How come I see it so much then?
Because people are addicted to their phones.
Yeah, absolutely. People can't separate themselves from the thing, even though they know they shouldn't be doing it. Okay? It's harder to break the habit of people texting and driving than drinking and driving. Okay? There are far less intoxicated drivers than there are distracted drivers on the road. You know what the worst part of that is? Drunk is less dangerous. If you're drunk and driving, which obviously you wouldn't do because everybody knows better, okay? But if you're drunk and driving, your reaction is slowed, but you'll react. Someone who's not looking at the road because they're looking at their phone doesn't react until they hear the thud. Okay, or crash or whatever it is. Hopefully it's a crash and not a thud. Okay, because they're not even paying attention at all. Okay, like a drunk will react, but they'll react late. A distracted driver doesn't react at all because they just miss it. Okay, now I'm going to show you just how much worse your reaction time gets when you're distracted by your phone. Who wants to be my volunteer? There's nothing embarrassing about it. Okay, please. Okay. So we're going to do a control here first. Okay, you're right-handed, right? Mm-hmm. Okay, so I'm just going to hold your hand out over the edge of your desk and like you're going to grab this. I'm just going to hold it right above your hand. Okay? All right, so Reese is watching. I have the right way. Okay, she's watching what she's doing. She's paying really close attention, and she's going to grab this ruler when I drop it. Okay, right now I'm just going to keep talking so she doesn't really know when I'm going to drop it, and she's, but she's paying close attention. Okay, so you fell 33 centimeters in the time it took her to react to the fact that it was falling. Okay, now take out your phone. And do whatever you do on your phone with your left hand. Because you'll have to, and I won't watch what you're doing. Oh, I hit the binder. Shoot, you didn't have it off far enough. Whoa, not bad. It was almost exactly the same. But I dropped it right as she was checking to see if I was gonna drop it. Okay, you got, okay, does someone else in here message you? Yeah. Okay, whoever that someone is. I wanna have you guys have a conversation, because that's usually what people are doing. Okay. Put your hand a little further over. There you go. 55. That's actually one of the best ones. I once had one that did this. Oh! Like it literally, it bounced, and then they were like, oh, what's that? And I'm like, that's the thud of the kid you ran over. Okay? So you didn't do too bad, but still, it fell almost twice as far before she grabbed it. Okay? And she wasn't completely enamored of her phone, but like fairly distracted. All right? I mean, you've probably all seen it, but you've seen that person and they're not at all paying attention to what's going on around them, and they're wandering in and out of their lane. It's really, really dangerous, okay, to not be looking at the road when your car is moving. Okay? You'd think people would be kind of more aware of that, but okay, it's something to be aware of. Okay, and this was kind of a safe, controlled environment, and Reese did a good job of catching that. Okay, but it's certainly not always that way. Okay, people can become very, very distracted and run into the back of people. So anytime there's a rear end collision, you can almost bet that was somebody who was texting while they were supposed to be paying attention. Right? But it's super dangerous, especially in playground zones, in school zones. Yeah, okay. I actually once saw a lady in the Westmount school zone. There was a police officer there doing a speed trap at 3:30 when school let out. He clocked her. He stepped out into the road to wave her down and had to jump to avoid being run down by her going 60 through the school zone. He got in the car and had to go after her. She never even knew because she was like that. Like I could see the whole thing happen, and she was just, you could tell she wasn't paying any attention at all. Double the speed limit on a school day when kids were getting let out, nearly ran a cop over. Okay, yeah. Hopefully she was never allowed to drive again. Okay, and that's the kind of thing that says you just don't deserve a license. Driving is a privilege, not a right. Okay, so yeah. You're all going to be getting your license probably in the next little while. It is a big responsibility. Treat it as such. It can be fun. Driving is fun. Unless it's in traffic, then it sucks. But it can be fun. But remember, it's a big responsibility. Your car is a weapon. Okay? It's heavy, it's fast, it can hurt people. Okay? You have to be careful with it. Yeah? Okay. All right, let's try this one. This is more about reading a clock than anything else. Okay? Yes, you can. Okay, 1,500-meter race. Said Ayueta was a Kenyan runner. Oh, this is the big Kenyan runner. Okay, and he was one of the first people to use altitude training. Okay? And as a result, was very fast in the middle distances. Okay, so 1,500 meters in 3 minutes, 29.46 seconds. Okay, you'll have to convert that all into seconds. How many seconds in 3 minutes? 180. Okay, so 180 plus the 29.46 seconds. Okay, is this one about as easy as they get?
Pretty much.
Okay, it is, yeah, because I don't even have to manipulate the formula. Now, none of these have had vectors in them, have they?
No,
Would that change some of what we do?
maybe.
Yeah, it might. I mean, if it's something like this, like I would still just divide all the numbers. I would just have to make sure I put what on the end?
The directions.
The direction, yeah. A one-step question isn't really much different other than you have to remember to put a vector on, okay? But in this one here, we're just looking for the speed. We know the distance is 1,500 meters, okay? And we are looking at 209.46 seconds, if my math is right. Okay? And so when we divide those two, we get 7.16 meters per second, which may not sound fast, but that's 3 3/4 laps of the track out back at 7.16 meters per second. And as someone who coached track and field for a lot of years, I can tell you that that's super fast, because I never saw anybody go under 4 minutes in a 1,500 meter. Okay, that's 30 seconds faster than that. I think the record now is like 3:18 or something ridiculous. So it's super fast. It's basically watching somebody sprint 3 3/4 laps. Okay, at full tilt. It's crazy. All right, now I got one here that's a two-parter. That's the one. Okay, so this one's 2 parts. Okay, and then I'm going to get you into some that are vector related. This one's very similar to the first question on the quiz.
Is it possible to make the font bigger?
Okay, let's have a look at this one. So, just like the one on the quiz, we got a part 1 and we got a part 2. But this is one of the kind of easy vector ones because the parachutist doesn't change direction. They're always falling down. So all we have to do is remember to write down at the end. Okay. So they fall with the parachute unopened, 625 meters down. Okay, in 15 seconds. And then they open the parachute and they only fall 356 meters down in 142 seconds. All right, we want to find the average velocity. Okay, we need total displacement and total time. Since we only have the displacements in time, we don't have to do anything other than add them up. All right, so 625 plus 356 is 981, right? I think 981. Okay, and then we're going to be dividing that by 157 seconds. Okay, so when we do that, we should get 6.25 meters per second down. Okay, now that one's a bit easier because, as I said, they don't change direction, so I don't have to remember that, you know, there was an up and a down like in the elevator question we did yesterday. Okay, but in every other way, it's pretty much the same as that one. All right, questions on that one?
When you're writing it out, if you don't put the little arrows over top of the D and the B for your given, so you can lose marks.
No, I wouldn't have you lose marks. I would just worry that you might get them confused at some point. But Yeah, in the end, if you've got the right method and the right answer, I'm okay with that. I don't always write them, but. Oh, man. Oh, I didn't realize I messed that up real bad. Okay, so, car makes a 60-kilometer trip. That's the total displacement, okay? With an average velocity of 40 kilometers per hour in the direction due north. Okay? There's no change in direction in this question, so you don't have to worry about anything being negative. Okay? The trip consists of 3 parts. The car moves at a constant velocity of 25 kilometers per hour due north for the first 15 kilometers. 62 kilometers per hour due north for the next 32 kilometers. At what velocity does the car travel for the last 13 kilometers? Okay, so let's just write out the givens together here just so we can kind of see it. Okay, in part 1, we know the velocity is 25 kilometers per hour north, and the displacement is 15 kilometers north. In the second part, we've got an average velocity of 62 kilometers per hour north, and the displacement is 32 kilometers north. Part 3, all we know is it's 13 kilometers north. Average velocity over the whole trip is 60 kilometers per hour north. And the total, oh, whoops, sorry, I got that. Sorry, that's the, I got the numbers mixed up. Sorry, guys. Sorry, it's 40 kilometers per hour north. And the displacement is 60 kilometers north. Okay, so they want to know this. They want to know the velocity in part 3. Okay? In this one, they gave you the average velocity and the total displacement. Probably something you can find with those 2 numbers that might help you get V. What else do you need from part 3 to get V? Time. Okay. Can you find the time for the totals?
Yeah.
Can you find the time for part 2?
Yeah.
Can you find the time for part 1?
Yeah.
Find those times. They'll help you get the one you need. So if we're going to find the speed for part 3, we need to know the time for part 3. In order to find the time for part 3, we need to know how long the whole trip takes, as well as the other 2 parts. And then we can subtract those, and we'll know what's left. Whatever's left is how long part 3 takes. Okay? So I'm going to find the time here. That's going to be 60, that's the D, over V, 40, which is going to be 1.5 hours. Then I got to go back to part 1 and part 2 and do the same thing. So T is going to equal 15 kilometers over 25 kilometers per hour. Now, here's the thing I actually wanted to use this question for. Okay, 15 divided by 25, okay, is 0.6 hours. Okay, and in part 2, okay, it's 32 over 62. Which is 0.5161290. I got to keep all of those. Okay? When you're doing physics, don't round off until your final answer. Everything matters. Okay? All of those things are measured. All of those things matter until the end when you round off your final answer. Okay? It does make a big difference if you round them off, especially if, like we were doing something later on in the unit, like energy, where I have to square something. If I round this off and then square it, it's going to be even more altering, okay, than if I left everything. Okay, so always keep all your decimals until the very end. So I might not write them all, I never do on the board, I would write 0.516 and just leave it there, but I'm gonna keep the number in my calculator. Okay. All right, now that I've got that, now I can figure out what my leftover time is. Okay, so I'm gonna take my 1.5 and I'm gonna subtract that number. And then I'm gonna subtract 0.6 as well. All right, so there's what's left. That's the time for part 3. 0.38387, blah, 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 okay, hours. Okay, I'm not gonna write all the decimals, I'm just gonna write that and keep the number in my calculator. All right, V equals D over T. So I take my 13 kilometers, I divide it by 0.383 hours, and I'll get my final answer. So 13 divided by that number. Okay, and I get 33.8 meters per, actually 33.9 kilometers per hour. Oh, and I got something different here too. I don't know how that happened. Okay, did I find something wrong here? No, I kept all the decimals, that's what was different. Okay, everybody all right with that? So important to keep all the decimals. Okay, most of the time, it's not gonna make a huge difference and I'll know what happened, but sometimes, especially if you end up having to square something later, it does make a big difference. So always try and keep your decimals until the very end. Okay, that's pretty easy in their modern calculators and to keep those decimals. All right, tomorrow, we are going to start looking at position versus time graphs. And we'll be doing a lab on that early next week, probably Tuesday. All right, good work today, guys.